Hello everyone and welcome back to lecture 5. And in this part we are going to look at how we can actually calculate the heat transfer between two systems in an enclosed system. Okay, so in the previous part we look at what are, for example, black bodies and gray bodies and how we can calculate the heat emission from a body by using Stephen's Boltzmann law. And we said that for the case of, for example, black body, the energy emitted will be EB is equal to sigma times T raised to the power 4. While if we are talking about a gray body, the energy EG would be equal to epsilon times EB, and this epsilon here is actually the fraction of the energy that is going to be emitted by the gray body compared to the black body. Okay, and this epsilon is given in between the value of 0 and 1. So it means that if you are have a value of epsilon 1, you are actually considering a black body, but if you are far from a value of 1, then you are actually going towards non-ideal behavior. Okay, and this epsilon has no units. So this is more or less what we talked about in the previous parts. Now we are going to talk about that. Okay, the object, for example, is emitting a radiation, and if that radiation is going to fall on another object, what is going to happen to that object? Okay, and here, for example, just like the previous case, we have when we have radiation or incident radiation emitted by an object and it falls on another object, the radiation is going to be absorbed by the other object. Okay, but the extent to which this other object can absorb the incident radiation depends on the nature of the object. Okay, so for example, once again, it is if it is a black body or if it is a gray body. Okay, so a black body is going to absorb all the radiations, the incident radiations, while the gray body is going to only absorb a fraction or a certain proportion of that incident radiation. Okay, and a common example is, for example, here that is like shown. So, for example, if you have a light source or a source of radiation, and then you have two different objects, one is a black body and the other one is a gray body or a shiny surface. And if you look at these two objects, you can see that the temperature of the black body will increase much quickly and to a higher extent compared to the temperature of the shiny surface. Okay, and you can also, maybe you might have observed this thing. For example, if people who have black cars or people who have white cars, so the black cars, for example, they heat up quite a lot compared to white cars or shiny gray cars, because the black color of the car is going to absorb all the heat. Okay, and so this is, again, it goes back to the nature of the surface, if it is a gray body or a black body. So if you have, for example, a black body, so all the incident radiation is going to be absorbed. So for example, you have this body here and you have certain, for example, radiation that is kind of falling on this object. So if this object is a black body, all the energy that is in the incident radiation, that is Q incident, will be absorbed by the body, and that it means the Q incident should be equal to Q absorption. Okay, while for the case of a gray body, the amount of, for example, energy that is absorbed by the object will not be equal to the amount of energy in the incident radiations, and only a fraction of the incident radiations or incident energy is going to be absorbed. And we can express that by using this factor here, alpha. Okay, and this alpha is the absorptivity of the surface. Okay, so what it defines that to what extent the gray body is going to absorb the incident radiation as compared to a black body. Okay, and again, just like epsilon, the alpha is a constant. Okay, and it has a unit between 0 and 1. Okay, it has a value between 0 and 1, and it has no units. Okay, now in most of the calculations, alpha is not equal to epsilon, because they are two different properties of the material. But if, for example, you have there can be situation where the epsilon is actually equal to alpha. So it means that the absorptivity and the emittivity of the object is equal. If the two objects have identical temperature and they are emitting light and absorbing light at the same radiation wavelength. Okay, and what it means that a perfect absorber is also a perfect emitter. Okay, so we can only use this relation that is known as Kirchhoff's law, that in case where alpha is equal to epsilon, and that is only possible if the two objects have same temperature and if they are emitting and receiving the light at the same wavelength. Okay, so what we discussed so far is that for the case of emission, we can use Stephen Boltzmann law, and we can express the thermal energy emitted by the object by this relation here. Okay, so that is the energy coming out of the object. Okay, that is the energy coming out of the object. While for the case of absorption, we are looking at the energy that is actually being absorbed by the object. Okay, so for that, we are using this relation here, where we are using this property alpha, okay, to see that to what level the heat energy is going to be absorbed by the object. Okay, so as we discussed in part 1 as well, that radiation or the use of radiations is quite common in our daily life. For example, one of the common application is sauna beds, for example, where people use, for example, sauna bed to get tanned, because in UK there is not so much sun, so a lot of people are using these artificial tanning, for example, systems. But obviously we have to be careful that we are using the right bed for that. The other application, they're very common in the UK as well, again, because there is limited sun. So a lot of people are using greenhouse. For example, they build greenhouse to grow their plants. And the reason is that when the sun's energy, for example, the radiation enters this greenhouse, when they hit different objects, their wavelength change. And because of the wavelength change, the property of this glass material to actually absorb and emit these radiation change as well. So the glass is going to absorb, or this system is going to absorb a lot of energy and only going to transmit a fraction of that. Okay, so this is another way of actually playing with the emissivity and absorptivity of your system to use it for your advantage, and in this case to grow plants. Another industrial application, for example, of radiation is to use radiations to measure the temperature. Okay, and we also discussed that, for example, in metal processing or glass processing plants, the temperature increases to very high temperatures like 2000 to 3000 degrees centigrade. And if we use a simple thermometer or a thermocouple, it will melt, because the whole idea is to melt the metal. So in this kind of plants, we use another, for example, kind of thermometer that is called pyrometer. And this pyrometer uses the concept of heat radiation. So how it works is that, for example, you uh, emit a certain wavelength of energy, and when it hits this hot object, that is going to change the wavelength and the degree to which this object is going to actually absorb this radiation. So based on the wavelength and the amount of heat emitted or absorbed by this object, you can tell what is the temperature of the object. Similarly, you might have seen these laser guns. You point a laser on an object, and actually it can tells you that what is the temperature of the object. So this is exactly the same concept here, that the laser is the light radiation that is going at a certain temperature and a wavelength, and then depending on what object it hits, it change in its properties, and that based on that change, you can tell what is the temperature of that object.